Hello, I'd like to welcome you to my lab, and today I like to present our Turtle LoRa peer-to-peer boards, and this video will all be about programming these boards and the libraries behind this. It's all done in Mbed OS, and I will show you Mbed Studio, how this can be done, and give you a tour about the background of all these libraries running on this, USB support, radio support, and regular timers, etc. And all this will be a little bit a nice tour done via the Mbed OS Mbed Studio tool. So let's get started. Go into the slides. I like to give you a little bit information about this. We got this Mbed OS from mbed.com, and here you can download everything. It's necessary to set up an account, but then the whole stuff is for free. I will not dive into this at this moment. I will launch the Mbed Studio. This is a local IDE where I can basically just import the software, which I have already done here. I compile this and it's getting compiled. Again, this works very quick because I did this already in the past. So this is my binary here. I can open a terminal window and see my sample application for the turtle board called turtle.bin. Now I start the downloader, put the board into programming mode, which I have done now, hopefully. Yep. And burn the software into the board, which is completed by now. Now a terminal will appear. You can use TerraTerm or another application on Windows. On Mac we have this already built in. And here we have our application with a lot of sample programs, and I will check this out with you, but this is just the start to see how this works. Basically programming, flashing, and the application runs. If you don't do anything, it starts up with a sample application. So I think we dive into the details now. So let's go into the next section. Welcome to my RadioShuttle tour. This is a tutorial about programming software for the turtle board using Mbed OS and its tools. This is the actual board, and just to explain it, here we have an SMA antenna with an antenna included, the LoRa chip, the CPU chip, the STM32 CPU chip, and a debugging connector, a user button and a reset button, and the USB connector for programming this board and configuring the board, as well as getting log files logged via virtual COM to the USB port. So what do you need to get started? An Mbed account is required to download the Mbed utilities and use the online IDE. Firmware download of the STM32 utility is needed. We have a nice utility developed by RadioShuttle to flash the board, to flash the software into the board. Of course, the turtle board. A pair of 2 or 3 makes sense to start with. A micro USB cable to connect to your PC, and a Windows or Mac workstation. Linux will work as well. However, I have not done much testing on Linux, mostly Mac and Windows. For Windows, it's recommended to use TerraTerm as a terminal emulator, and Mac OS something like this is built in. So there are 3 different development environments. It's actually C++ development. Mbed is a great system utilizing C++ features. There is the online IDE. It's a web-based user interface. The benefit is it uses the ARM compiler. It's all integrated. There is no need to set up anything on your local PC or Mac. I use this for years. It works very nicely, and I'm happy with this. So there's a new integrated development environment, the Mbed Studio. This is new. It comes with the ARM compiler and everything needed to develop software locally on your Mac or PC. And this can be downloaded here. And there's the third option, the Mbed OS command line environment. And I will give you a tour about the 3 development tools, and later on I continue with the Mbed Studio only. So that's Mbed Studio. Let's start first with Mbed OS, the online compiler. On the Mbed website, once you have an account and you log in, there's a tab compiler, and I can click on this compiler. On the left hand I see all my projects. I have here, not this one, this one, a project where the current RadioShuttle sample software is sitting or waiting for me, and I can see all the different libraries, a folder with utility files, and the main code. So what's very nice, I can just select the project, click on compile. It compiles everything on the ARM Mbed server, which is their cloud compile system. And once it's completed, it's uploaded, and I can see it here. Here is my file. And let's start the Flash utility. And I turn the board into programming mode and drag and drop the compiled application on this utility, and it's completed. Now I can open a terminal window. Okay, here it is. Here I see the start screen of the application, and I can decide to run the temperature sensor, like T for temperature sensor, or P for property editor, or K for the RadioShuttle remote relay sample. And I will get into the samples a little bit later. So just for now that you see how this works. Okay, so this works great. Let's go to the next environment. And this is the Mbed Studio. In Mbed Studio, it's very similar. On the left hand, we have our projects, multiple projects. I checked out the Turtle project. I can click on compile. It will compile the project. I did this already in, let's say, 10 minutes ago. Therefore, it's all cached. There's not much to do. After it's completed, it shows me the binary path and the size. I have set it up a terminal here to open the window where the file is arrived. So now it's 136 kilobytes in size. I can switch the board into programming mode, which means it will show here that it's ready for flashing, and drag and drop the file to the Flash utility, and now it's completed. Let's connect to the virtual console, and now I can run again my temperature sensor or whatever kind of stuff I like to do. Just as a side note, if I don't do anything, there's a default application which can be configured, and this will start automatically after 10 seconds. Okay, so this is how it works with the Mbed Studio. Now I like to show the third option, and this is the GNU offline compiler. They call it Mbed development tools, command line tools, and here I can just type in Mbed compile. It compiles my project, and here I see the whole thing. Again, the file, and I can just open this folder. So here it is, and same thing to drag and drop this after putting the board into programming mode, and drag and drop this to the device, and this downloads this, and now I can connect via the terminal, and yeah, we are all set. Here we can easily see all libraries, and I will get back to this libraries in a minute. So just let me go back to slides. So you saw the 3 different development environments. For starting, the online compiler is fine, and for professional working, I think the Mbed Studio is very nice, and I'm used to command line utilities, and I use mostly this one, but more and more I switch over to the Mbed Studio. So I just recap what needs to be done. So once in Mbed Studio or in the Mbed Online IDE, you set up a new project and you specify the URL where this should be imported from. That's the GitHub URL. And once this is done, it's getting all imported into the IDE. And the next step is to compile it. And once it's finished, you will see this kind of message here with the binary, and via drag and drop you can upload this to the STM32 utility. So this utility we developed for Windows, Mac and Linux, and it's very powerful and very easy to use and very, very fast. And it has some nice benefits that properties which are saved at the end of the flash memory will not be erased when you upload a new file, so all settings will stay. I have a different video on properties, and we'll get back to this properties a little bit later, but the properties itself are a different video, and I will link this to this video. Okay, so flashing this to the board, I believe you saw everything live. There's really not much to tell you about it. It's just turning the board into programming mode by holding the user button, and once pressing the reset button, this will turn the board into DFU boot mode, and in this boot mode our flash utility will communicate with the board and will be able to flash data to the board, and after uploading is completed, it will reset and start the application. Okay, so you saw this multiple times. After the software has been uploaded to the board, we have a little terminal included to show you the different applications, sample applications on the board. Of course, you can configure it to remove all applications you don't need, or you can add your own ones, stuff like this. On Mac, it's done with the Mac terminal. On Windows, use TerraTerm to connect to this. And this gets done via a virtual COM application, where we basically simulate on the board via USB a virtual COM device. So the next step is I like to explain you how the software works and give you an insight about the details of the software. So the main application, I need to explain the main loop, what the application is doing. So it starts, it inits the serial devices like USB and UART, and then it runs this command interpreter. You remember where you can specify what kind of application you like to run. And once you select something, it goes into an infinite loop. And this loop stays the same for the entire program. And basically it waits in a sleep or deep sleep for interrupts, timers, button presses, which are interrupts again. and then it processes this interrupts and processes the program, and once it's completed, it goes back to sleep. So this means sleep, wake up, processing, sleep, wake up, processing, sleep. So we have a little green LED, and when we go into sleep, we turn the LED off, and when we do something, we turn the LED on, and after the processing is completed, we turn it, when we go back to sleep, back to off again. This sleep will be a regular low power sleep, and if you specify node offline, which is a deep sleep configuration, then the sleep turns into a deep sleep, which means everything is turned off except for keeping the memory state of this MCU. And once something is happening, like a timer or a user press or some other event, it takes a few microseconds, and then it processes this and may go to sleep again, or it's putting out some data, and after this is finished, it goes into deep sleep. So this loop is very, very important, because you don't like to do synchronous waiting or processing. Everything needs to be done asynchronously with timers and with callback functions, just to make sure that you sleep all day long to save energy for this board. So this is the main loop. A very similar loop you have in Arduino. The initial part is called setup, and the infinite loop, it's called loop. However, Arduino does not have this sleep capabilities. We added this capabilities with our EcoPower and Eagle boards, but that's a different topic. We are now focusing here on the Mbed OS Turtle board. Okay, so that's the main part. Let's go to the next. And now we look into the software a little bit more in detail. So we can see we have multiple libraries here: the Mbed OS operating system, a special buffered serial library, the LoRa driver, the RadioShuttle protocol, the USB device support, and the virtual COM driver. Another library, the properties, and another library, the sensor library for the temperature and humidity sensor, and the OLED display driver. So this is basically common libraries we deliver. By the way, all the gray part, the light gray here, it's all delivered by RadioShuttle and developed by RadioShuttle, except for this buffered serial. This comes from Mbed OS, has been enhanced a little bit, but everything else we developed. And the operating system, Mbed OS, is the operating system underneath. And the beauty with Mbed OS is you can swap out the operating system for a different board type. Let's say instead of an STM32, an NXP processor, or an STM32L0 processor, whatever, and the whole thing should stay compatible with this, because the Mbed OS is the operating system underneath. So now go to the flow, how the software works. The main, I explained it earlier, what we do with setup, etc. We have a couple of utility functions to set the clock, to manage the RTC clocks, and to the command interpreter. And then we have a very thin program called programs.cpp. And this programs is a kind of interface for multiple program modules. And these modules use all in common the radio base, which is the C++ base class for all these modules, to avoid that we need to reinvent the same code for every single demo application. So you may recall, and I will show this here, that we have multiple applications like the properties editor, LoRa ping pong, the continuous, the blinky test, the radio test, new stuff like this. And these are the different modules here. And I will show this in more detail later. Before I show this in the code form, I will just go over it. and explain it. So when you like to do a new project for radio shuttle communication, talking with a server or peer-to-peer communication, the radio test new is the best sample to start with. It's a peer-to-peer application, which means it can receive and send data, and you can send any kind of messages between nodes or send out a broadcast. All this is covered in this application. Then for starters, we have a very simple application. It's a blinking application which just blinks an LED. But it's a little bit nicer than just blinking, because the blinking gets done via timers and everything gets done asynchronously, which means during the blink phase, the whole board will go into deep sleep mode, and when the next timer occurs and blinking is over, it just turns off the blink, etc. So just to get a very basic example, we included this. We have another nice example. This is the remote temperature sensor. It's a turnkey sample application supporting the humidity and temperature sensor. So just connect the sensor to the board, run this application, and every 10 minutes you receive a report about the temperature and humidity and battery state of this sensor. Remote relay is another very nice application where you basically use two boards. One board is a relay board where you put a regular relay to it, and another board you have maybe some contacts, buttons, whatever, and when something is clicked, the relay at the other end will open or close. So a very nice application, because when you have a signal at one end, via LoRa you can transfer this, and a relay can turn off a pump or a motor or whatever, a door, a gate, whatever is needed. Then we have another very nice sample application. It's called Panic Button. And this Panic Button is a deep sleep application which stays forever in deep sleep. And when you click on the user button, it sends a panic message, a kind of emergency message to the other side, which may be the same board or a different board. And while it's transmitting the panic message, I have panic, I need help, you can connect a buzzer to this to do some beep tones. So basically, when your mother-in-law uses this device and she presses the panic button, that she receives audio feedback like a ringtone that the message is on its way, and a confirmation tone that it's completed and that the message arrived and help is on its way. So we have another nice application, that's the property editor, and I have to say a little bit more about properties later on, but I have a different video on it. With the property editor, you can set up all kinds of settings, including passwords and default applications, time zones, whatever you have in properties. And this property editor stores this in the upper part of the flash, which means when you reprogram the board, all the settings will be preserved. So LoRa Ping Pong, that's another sample application, but this is without a protocol, just sending out raw LoRa packets. Without node numbers, just sending out a broadcast packet, and a second board with the same application listen to this. This is the Semtech chip provider of the LoRa chip. They have a sample application. I ported this here, so that this can be used. CPU bench is a little application to do some benchmarking of this little MCU. And then the radio continuous TX. It's an forever transmitting application which can be used to test antennas and adjust the impedance of the PCB, etc., where you need to have a continuous signal. Anyways, there are plenty of nice turnkey applications and some utility applications. So I believe I explained everything from this point of view. So this is huge. We have decided to include all the different sample applications in one binary, which means it's easy to use. On Arduino, we have different sketches or programs for every single sample. There's a different program, and of course there are shared libraries like in Mbed OS. For the turtle board, we have decided to include everything in a single image to make it easy to start and to make it easy to use this even without programming. I continue here. One or the other viewer may think, why is this guy not just using full screen mode in Keynote, which is the presentation software, and I'm not doing this because the screen recording software I have running in the background somehow gets confused when I run into full screen, and then I have trouble with the recording. Therefore, I just show it here. Okay, so we saw the different applications, and here is a little list about the applications. I explained it already a lot, so I don't think that I need to dive into this. You can pause the screen and read it, to learn about it. So there's another topic. We have a property editor where we can set all kind of properties, and the properties are kind of settings like you know it from the Windows registry editor, where you have some keys and values, or Unix environment variables, name equals value, something similar we got here with the property editor. And we have plenty of settings, but let's say to get started, you need to know the remote ID you are communicating with for a node. Therefore, we specify here the node ID. And for the radio type, we have different radio types like an online node, an offline node, and a basic node and a server node. You need to decide what kind of configuration you like to run here. And node offline is good for energy saving. Node online is good to stay always online. And I'm going to show you how this property stuff works. So I downloaded the software, and now I should be able to connect to the terminal. Here we have this. We got one menu here called P for property editor. I can go into P. And just as a side note, it's the same stuff on Arduino for the different boards. We have like the EcoPower board and the server board, the Eagle board. Even the longer board works with this property editor. So I can type list to show all the properties. And here there is remote ID. Let's say I like to change this to 123, or let's say 12, just to set the ID 12 to something. And so set 12 equal 1024. And so check this out. Okay, it's set to 1024. And the radio type, I can set this to a different one. I don't need to do this, but let's say we have plenty of options, and these options are stored in the property area, and this is in the upper flash memory. And when stuff gets updated via a software update, this flash memory gets preserved, that properties are still available. And of course, when I return here and I start something and click on the user button, now it sends a message to the destination 1024. Right now there is no server or no counterpart. And actually I got something in here from a different system, but that's not our device. Okay, so you learned this property stuff. Back to the slides. So the next thing is I like to take a sample application, and I use the easiest one we have. It's this Blinky, which blinks the LED, and I like to create a own version of it, basically copying the example and creating a customized one. So this is very easy. I just need to copy the example, and then I can change it to my new name, whatever, and some renaming needs to be done, and yeah, you can read the slide. At the end it needs to be added to the program list, and I give it a try to do this. Okay, let's give it a try and duplicate this Blinky to a new Blinky. So here is the Mbed IDE, and I just open this here. For me it's sometimes a little bit easier in the Finder. I have this two Blinkies here, and I rename it into new Blinky. Okay, so this looks okay. Let's continue here. Here I have my new Blinky, and basically I take the Blinky name and rename the class to new Blinky. Just as a side note, this is the header file for the Blinky application. The new Blinky extends radio base, and this implements the programming interface. It comes with a couple of functions defined in the programming interface: the constructor, startup, shutdown, and service execute command, and the help text, and some local variables. I can just specify, okay, the blink interval should be 1 second instead of 2 seconds. So we have done this. Now let's go into the C++ code. Instead of including Blinky, we include the new Blinky, and this is also called new Blinky. Here it's called new Blinky. The shortcut for the program menu, let's take an uppercase U, and so that's the new Blinky. Here the startup function, which is basically every time something starts, stuff needs to be initialized here. The same for shutdown. When an application stops, usually it never stops, but it can be done to quit this, and then this is the shutdown procedure. And when it's getting started, it's called execute. It receives a couple of command parameters. And so now this is all renamed, and well, let's give it a try. So now let's see, new Blinky 68. Yep, this needs to be called new Blinky as well. And I will explain the code in a minute. So now this is completed. The new Blinky is compiled. And let's switch turtle build nucleo take this and turn the board into programming mode by holding down the user button and click the reset button once. So now we flash the new program we just compiled with the new Blinky, and Voila. Where is the new Blinky? Ah, the new Blinky is still not there. I can tell you why. And we missed one thing to do. And this is the file programs.cpp. Oops, no. Programs.cpp. And here we include everything. And of course, we need to include the new Blinky. And later on, we define the application. This is basically the constructor, the class. And this is supposed to be called new Blinky and my new Blinky. Okay. Give it another try. And refresh the application. Okay. Voila, the new U is here and I can run this program and it starts the new Blinky. So very cool. And so you saw it works, and now I like to explain a little bit what the Blinky application is doing. And I'm just using the Blinky, the basic application, to allow you to follow me and to get an idea what this application is doing. So I just quit this and go here. So I started with the .h file, basically the class, and I explained this a little bit already. So now I go to the C++ part, and this has a kind of help text for the Blinky. This is when you type in the command interpreter help U for the new Blinky, then you receive this information here. Then the next thing is, this is the C++ class new Blinky. It inherits program interface, and it sets a name, and it sets a shortcut how it will appear in the menu. So let it ring. The startup is when the system starts, it gives arguments to the application, so you can call it U for the new Blinky, and then you can add parameters, and you will get this with argc and argv, pretty much like a C application where you have arguments. And in this case, we turn on one application called init the LoRa chip and shut down it. This is because by default LoRa works right away and receives and is able to send, and to avoid that the LoRa chip eats our battery, we just turn it off. Then we have an LED which we initialize here. We have a timeout where we create a new low power timeout. We say this application is active, and that's it for the startup. Shut down, we just delete our resources or free our resources. For the LED, it's getting freed. The timer, it's getting stopped and freed, and is active, gets to false. So very easy. When the Blinky commands gets executed, so initializing is one thing, shut down another, and executing is a kind of run method. And when it's getting executed, then it calls blink update, and it turns on the LED and calls blink update, and we will see this in a second. So the blink update is just sending us, this is the interrupt function for when an interrupt comes in, it sends us a kind of soft interrupt, and with an interrupt timeout. So in this we receive here in the service routine, we receive the interrupt timeout, and we basically, when the LED is turned on, we turn it off, else if it's turned off already, we turn it on. And here we specify add a callback to this after a period of time. This period of time we specified here. The blink duration is 20 milliseconds and the interval is 1 second. So here we specify the interval and the blink duration. This basically means the timer, we turn, in this case here, we turn the LED on and the timer calls us in 20 milliseconds. And we return here and the main loop goes back into sleep after the service is done. And it will be called again with blink update with the interrupt, and this will call the service routine, and this will next time turn the LED off and restarts a new timer. So this is how the whole thing works, and I think it's very straightforward. And you remember that I explained something about the main loop, where the main loop just initializes some stuff like we do here, and then it runs forever in this while true loop. And this is basically going into sleep all day long until an interrupt occurs, and if an interrupt occurs, it's processing this interrupt, it checks out what kind of program is active and services this program with the pending interrupt. So this is how it works. So I believe with the Blinky we completed this, and this is straightforward, and you saw how easy it is to do something like this. So I go into another application. It's called Radio Test, and when we look to the .h file, you see the same thing. Name extends radio base and program interface, the startup, shutdown, and service routine, the execute routine. Stuff gets defined here. And in Radio Test itself, it's very similar. Only a very few classes and, or let's say, member functions. And when a key is being pressed, we send out a basic message with this RS send message. When we are a server, we send this message. When we are in a node, we send this message. It's just a very, very basic example to show you how to send LoRa messages. And you send this with this message to the remote ID specified in the preferences. So this will, or in the properties, this will be initialized before the app starts. Okay, so I think we have done a good job on explaining this, and of course this is all a lot. Maybe I switch one more time to programs.c. You remember that I was adding the new Blinky here. This is the class for the Blinky example, and this static class here just defines it, that it's active. So let's assume you don't like to have all these applications in there. You just command out everything you don't like to have. And then, let's turn off everything except for the temperature sensor, and the LoRa ping pong can be turned off as well. The property editor, it's always good to keep this in there. So save this. And last time the application was 136 kilobyte in size. Now let's compile this. And suddenly it's only 126 kilobytes in size because all the other applications are omitted. Okay, so I just undo this, undo this, and let's go back to slides to see what else we have. So the Blinky stuff you learned, and I think here is the guide what to do to duplicate an example. So let's wrap up. In total, I think it's very easy to get started because we have plenty of sample applications and all are flashed into the single board, so that's easy. The whole thing, the turtle board, is very, very energy efficient. So let's look to this board. With this board, we just need a few microamperes in deep sleep, which means the board will easily be available for more than 10 years of operation. Let's say sending every 30 minutes or 40 minutes a message to a server. A 10-year operation should be all fine. So it's very, very energy efficient. And it's efficient because we don't do any polling code. So it's all done asynchronously. It's all done with low power timers. We go automatic in deep sleep whenever it's possible. And yeah, as a result of good hardware engineering and very good software engineering, or actually the hardware is also very good. So yeah, we need only very few microamperes, maybe 3 microamperes, depending a little bit on the device. There's a little bit more room for optimization, but let's say 2-3 microamperes, this is nothing. The RadioShuttle tools, I think this is very, very easy to use and very, yeah, it's very sophisticated. Just using the I just wait a second. The virtual USB system to connect to the board, to configure it, to run the property editor, to upload new versions and stuff like this. I think it's unbeatable. The drag and drop, when we upload programs, you have seen this, we are talking about 2-3 seconds to upload a complete new program. So that's very cool and very, very fast. The C++ IDE, it's also very sophisticated. So for example, you can click on variables and specify go-to definition. Doing the editing of files or of code, it will give you already information about code completion, and when you enter some wrong variable names or invalid stuff, it will tell you this right away. You don't need to wait until the compiler starts compiling it. So in the background, it's pre-compiling it and gives you the information. So the Mbed Studio is really very, very nice, and the Mbed Online IDE. And as you know, I'm heavily using the command line version, which is the same stuff, so works really good. Mbed OS is a true operating system, and I show this one more time. This blue part here is the Mbed OS, and all the gray part is delivered with RadioShuttle. So, which means we can take our software and run it on a different board. Like we do this, we run it on the Arduino boards, but for Mbed we run this on the STM32L0 board and on other non-published board configurations, because Mbed OS gives us the same feature set: timers, GPIO, deep sleep, low power timers, the IDE. So it's everything the same. So I'm very happy about it. So yeah, let's say I think it's a very powerful system, very nice sample software, and of course the RadioShuttle protocol is unbeatable for peer-to-peer communication, and it's safe and secure. Let's check what else we have. For the property editor, I explained to you that we have a separate video on this, so check out this URL here to see to get a training on the non-volatile properties. And just as a side note, we have this available for all the Arduino boards and the Mbed board. It's the same code. And we got a very nice MQTT push client, or actually push app for Android and iOS. And it allows you to send push notifications to a smartphone via MQTT. And this I can probably show on the next slide. Yeah. So we have multiple boards here, and this goes to one Eagle board. This is our gateway board, and the Eagle board itself communicates via Wi-Fi, via an MQTT server, and we send push notifications to the smartphone. So this is very, very nice. Yeah, so in addition to the Turtle board, which is a perfect board for node applications, we have the Eagle board. This is, I just go and show you the Eagle board. So this is the Eagle board, comes with an OLED display, and it comes with Wi-Fi and LoRa combined in one board, and it's a simple, easy gateway board and forward stuff to MQTT. So check out the Eagle board. This time the training was focused on the Mbed OS board. Yeah, OLED display. This display here can be connected straight to the Turtle board, which means it's pin compatible. The 4 pins match the 4 pins on the board, and you can just solder a header to it and connect this to the board, so straightforward. We have a very nice temperature sensor, and it's the Z7021, and this is humidity and temperature sensor. It works very, very nicely, and it needs only a microampere or 1.5 microamperes in standby. The drivers for the OLED display and for the temperature sensor are included in the RadioShuttle project. You may remember this was here, the library for the sensor and the library for the OLED display. So these parts are available in our web store, online store at radioshuttle.de. Check this out. Yeah, I believe I'm done for today, and wish you good luck with your projects and happy programming. See you next time. Bye bye.